Okay, morning. So we're going to start the tutorials. And I think this week tutorial we will just discuss some of the questions. I think some of the questions are actually reserved. We do not want to reveal the information, the answers in public, but you can approach me to let me know which specific question you want to discuss. I'll generally choose some of the questions to discuss for the quizzes that you just had. Quiz 2, 3, 4. Okay, I think quiz 1 is a bit easy. All those are easy questions. We just look at some of the questions that you have encountered. Just checking my. Okay. So these are some of the questions that you've encountered. Okay, we're going to do a bit of discussion. Okay, so this serial interface is under the input output, and it's under that chapter together with the IOs and all these kind of things. So the statement, the question goes like this: there's a statement and there's a reason. Okay, serial interface is faster than parallel. Reason because serial interface does not have crosstalk. Okay, now the reason, the statement is wrong, but the second reason is actually quite valid, because when you have a serial interface, you have several lines. Let's say, for example, you have 8 lines, all right? And these 8 lines, when these 8 lines, they actually they transmit the data that will actually any type of electrical signal that has changes at a certain frequency, they actually emit a type of interference. Okay. Now this type of interference, we call it crosstalk, because you have 8 lines, so you have interference from all these 8 lines. But if you have a serial, the only line that actually change is the data line. Okay, whereas the ground line doesn't change, the power line does not change. Okay, so you only have receive and transmit for serial. There is a bit of crosstalk, but not as bad as parallel interface. Okay, so this is the statement is wrong, but the reason is correct. It means to say that this first statement is wrong, but second reason is correct. Okay, serial interfaces are preferred nowadays. Okay, reason is because I/O interface experience parallel I/O interface experience in interference. Now this one I actually explained earlier. Now one of the reason why we are I do not know. I'm just coming up with questions. As we go along, we can ask questions like this. Okay. Now, why do you think serial interface are much popular compared to parallel interface? There was a time that all the printers actually use parallel interface. Okay. But as our PC actually gets smaller, you can see that there is no more parallel ports or even serial ports. Okay, there used to be a time where PCs or laptops have actually serial interface. Okay, so you can connect it to RS-232. Basically, that's what I did for my postgraduate those days. I have a laptop that has a serial interface. Okay, so slowly from parallel they shifted to serial, and then nowadays everything is just USB. And probably sooner or later, everything will move into a smaller USB. Okay, because they try to keep everything small. And the one of the reasons why commercially serial interface are more popular than parallel is because you only have one line, so your port can be much smaller compared to your parallel. Okay, so serial interface are preferred nowadays. Okay, one of the reasons is because yes, commercially the ports are smaller. Second reason is because there's less crosstalk, like what we discussed in the first question. Okay, now the following happen when an interrupt is requested, except. So you guys have to read back the interrupt. Okay, the chapter on the interrupt, and go through the lecture. Now this you can refer to page 299. Okay, when the the status register is pushed onto the stack. Okay, so when you request an interrupt, let's say for example you're doing something, you're doing some calculations suddenly, there's an interrupt, whether it's IO interrupt or timer interrupt or whatsoever. The interrupt vector, you can see that ABC is actually in the mechanism. I already taught you guys the what happens when an interrupt is requested. Now this particular topic I want you guys to go and revisit because you know, these kind of questions can come out. You know, what happens? You know, it could be an essay. What happens when the interrupt is actually requested? Status register is pushed on the stack. Of course, if you don't push the status register in the stack, how do you go back to the state before before the interrupt happens? So you need to have status register, whatever the content, status register to be pushed on the stack, because you still have your calculation to continue on. Your main program, in the main program, the interrupt vector is loaded into the PC. Okay, of course, this is a true. The program counter is pushed onto the stack. Yes, this is one of the things that's covered in this book. The PC is actually cleared. Okay, so this is in a way, this D is the most inaccurate as compared to ABC. All right, so it's very obvious the answer is B, except. Okay, so the PC, yes, the PC is cleared, but not at the request level. Okay, so okay, so I want you guys to actually go back and revisit what happens in the interrupt phase, all right, to the status register and all these kind of things. Treat it as a revision. You have a few more weeks before final. Interrupts are called maskable when they can only interrupt if. All right. So you still remember, maskable interrupts are interrupt that can be disabled via the general interrupt enabler. Now, where is the general interrupt enabler? All right. So general interrupt enabler is actually in one of the bits of status register. Right. Now select one if, okay, enable and general interrupt enabler is bit is set in the status register. Yes, definitely this one, okay, because there are non-maskable interrupts that can be disabled, but you need to disable the non-maskable interrupt flag individually. All right, so maskable interrupt can be defined by interrupts that can be disabled via the general interrupt enabler. Right, so this one is quite obvious. I want you guys to look at all these questions, revise. The address of subroutine must be stored in, okay, this is interrupt vector. This is obvious. Now, I want you guys to read 314. It's also in my this week lecture. All right, I presented a table. These are all the tables for the interrupt vector. They could be IO interrupt, timer interrupt, watchdog interrupt. Every of these interrupt, they have an address. Okay. I think one of you actually shared with me in the middle of the night. I think it's one of the code doesn't work, but I suspected it could be the reset vectors or whatsoever that are you put the interrupt vector wrongly. All right, so you have a check at that. Also, in line with this, do revision on the IO interrupt. How to do IO interrupt? The template, okay, the template. So make sure you prepare for it. All right. The following modules can request for non-maskable interrupt except. So in another way, I put it in a more compact version. Now, which is not maskable interrupt? Which is non-maskable? Which is non-maskable? In another way, if you do negate, it means which is maskable interrupt. Okay. So oscillator fault, definitely this is non-maskable. Okay, it will straight away go to reset. Access violation to flash memory. Okay, so this is also, you can refer to the book. These are all non-maskable. Active age on okay, active age on external reset NMI. Okay, so this is a physical. If you can see in your MSP board, all right, in your MSP board, although this SEM you might not be able to touch the board, okay, but if you just Google, if you can Google the board, okay, there's a button called the reset button where you press straight away the MSP product will restart. Now that particular pin, particular button is connected to the reset non-maskable interrupt pin. Okay, so you and an active edge. Okay, so it's either positive to negative. I mean 5 volt to 0. That active edge active fall, it will go into your reset mode. Okay, so the only answer, the only maskable interrupt that you can see is actually B, because we already say there is a maskable interrupt service routine to clear the status register. So this one is actually maskable. So look at the questions carefully. A group of instructions that will be used repetitively in different locations of the program is called subroutine. You guys just learn about this you learn about this subroutine function in your previous programming with your LED. You also learn about this just this week. Okay, you can remember it's called the subroutine version for assembly. It's called the macro. Okay, so make sure you guys study these. This kind of questions can come out. Do not get caught in this kind of thing. I already warned you. Something like this can happen. Test your knowledge on macro, whether you know how to use it or not. Okay, maybe he introduced a code, ask you to troubleshoot why is this code not working. Could it be the macros is not called properly? Could it be termination of the macros is not done properly? Okay, which of the following command is used to stop a watchdog timer? This one you've coded a lot of times. Okay, the answer is A, and I just want in conjunction with this, I just want you guys to revisit the 16-bit watchdog timer. All right, which one does which? Okay, so there are a lot of bits in the watchdog timer register. Generally, the answer is A, because you've done it again and again. It becomes natural to you to be able to choose A. All right, so you want to disable the watchdog. Now, what if you don't disable the watchdog? I already mentioned this a lot of times. Okay, you need to service it. Which pin to service? Which register bit to service? That one, I need you guys to go and revisit back. We cannot be repeating these things again and again. Okay. Now, this is the following example. This is actually an IQ question. Okay. You have a code converted into machine language. Okay, the machine have 3 lines and broken to 16 bits. Okay, what is the opcode for the first line code? Okay, so these are all opcodes. Of course, it's given as a command. Okay, but just to show you, these are opcodes. You can see that. Okay, so this is the first line of the opcode. First line means this one, move. Okay, so what is the equivalent machine language for this move? You can see, okay, if you convert it into hex symbols, you know that it's very obvious. Okay, the only common is 4. Okay, so this is move, and we know that this mnemonics is actually converted into 4. That's why they actually give you 1, 2, 3. It's like a test question. It's a common sense. Okay, they know that you're not able to convert this into machine language. You will not memorize it in such a way, but just to show you, it's actually giving you a clue. Okay, since these are common and these are common, we know that the first line of the opcode is actually 4. I also want you guys to go and revisit the addressing mode in page 170. Okay, so you always have, let's take an example, move. Okay, you move a certain value to a certain register. That's called register mode, register addressing mode. And then you have index, where X, right, you can plus with whatever register value where X is stored as an extension. So if you have X as 3 and then you have a register value, so that particular value will be stored index from the register value. Okay, so let's say for example your register value is something something. Let's say A, all right, A. So the value will be stored in A plus X, all right, and then you have absolute at constant address stored. So this one using the address in this format. Okay, you have a variable pointed by the register, all right, means to say that whatever that is in this register, all right, whatever that's in this register, let's say I register is R6, the content of R6, that value will be put into the content of R6. Let's say, for example, the content of R6 is, let's say, AA, okay? So whatever value that you store, let's say move absolute value something to this alias Rn. So whatever the content of Rn is, whether it's AA, so that value will be stored in AA. Now this one is this one is something that less implemented. It's called incremental. Means to say that whatever value that you have in the Rn, every time you execute this addressing mode, it will auto increment. Means to say first time you use, it will plus 2. Second time you use, it will plus another 2, so on and so forth. So it will keep on auto incrementing. Okay, and this is the immediate value. Means to say that you store an immediate value into the register. Example, move, use this hashtag, okay, some value, okay, to R7. Means to say that this type of addressing is an indirect, immediate addressing mode. You have a immediate value. You always have a hashtag. So if the question asks you, what type of addressing mode, if you see this hashtag, that means to say that it's actually a value. Okay. Now for some homework, I just like you to do some homework. For IO, read out. I think this one more or less, if you've done your lab, okay, you should be able to already. If you have done your lab, you should be able to already do this. This one. Okay, if you have done your lab, okay, PX, PN, PX in is basically just a read register. Someone actually come and talk to me that they get confused with the LED blink codes and all these kind of things, because fundamentally you do not know what is this register for. Okay, so I suggest go back and read what is this register for before you actually attempt to look at the code. Okay, and then you also have this. All right, so please read out this for register. Okay, where X can be 1, 2, 3, etc., etc. Okay, so this is very important for you to understand codes. You can see that all the labs are just involving in these 3 things. You do not actually go beyond these few registers. It's so easy that I do not know why people still don't get it. Please, if you still don't understand your lab, start off with this 4 thing, and then you will feel more secure, more confidence to actually look at the lab instructions. Okay. Blink LED, generally I don't want you guys to memorize. Please go through, understand it. Assembly, understand your labs. Okay, so I'm going to make it very easy for you. You have to read every page in the assembly, understand your labs. These are the common assembly instructions that you're going to use. Jump, whatever instructions that you use. If you have done your lab, I think you're quite safe in this area. Okay, because there are a lot of things to read in the assembly. It's impossible for you to cover everything. So I suggest learn assembly by your codes, okay, your lab sessions. Interrupt, I want you guys to read up how it works, all right? The mechanism, what is involved, push what to the stack, then after that you pull or whatever. Okay, the architecture questions, these are more on the theoretical question. Hubbard, von Neumann, computer cycle, the register, specific register, and the general purpose register. Specific, which are specific registers, status register, etc. Okay, so these are only a few things that I want you to actually go through. So we'll be doing some revisions, okay, in the upcoming weeks. The syllabus is actually completed. Okay, so basically I can summarize the syllabus is more to interrupt, I/O, architecture, and then the following few lectures are basically just assembly. So your scope is basically very limited. All you need to do is just study some of these things. I will do a revision class. We have actually finished the syllabus. I'll do some revision class. So I hope that don't rely on last minute study. Okay, don't rely for my revision class and only read the revision slides. You will fail. Okay, I guarantee you, if you only rely on last minute revision, you will fail. Okay, so I suggest from today onwards, you have a few weeks. Okay, take notes. Okay, as you take down notes, it goes into your mind. All right. So I already give you some of the stuff to study, not limited to, but I will give you more. Okay, this week I want you guys to study this first. For those who don't care, it's okay. All right. But for those who care about their marks, please go through. All right. So I think that's all for today. Thank you for bearing with me. All right. Yeah, I think Dr. Filbert will give the instructions for the lab. I do not want to interfere. As for the lectures and the syllabus exams, those will come to me. All right. So thank you.